So let's start section 14.5, which is on solving nonlinear equations, systems of nonlinear equations. So systems of nonlinear equations. So let's recall systems of linear equations. With systems of linear equations, well, you can either have no solution, case of parallel lined parallel planes, one solution, the case of intersecting lines, intersecting planes, or an infinite number of solutions. The case of coincident lines, the case of coincident planes. Okay, and those are the only real three options that we had for linear equations. So systems of linear equations, they either could have 0, 1, or an infinite number of solutions. And that was it. Well, suppose I have some systems of nonlinear equations. So suppose I have, I don't know, maybe a parabola and a ellipse. Okay. Then in that case, you could have, well, maybe a parabola and some sort of ellipse, in which case you could have no solution, just like above. You could have a parabola and an ellipse where it just intersects at one place. And so you could also have one solution, just like above. But you could also have a parabola and an ellipse, let's say, intersecting at two places. So two solutions. Or maybe a parabola and an ellipse, let's say, intersecting here at three places. So you could have 1, 2, 3 solutions, or even possibly well, that doesn't look good. There. You could have 1, 2, 3, 4 solutions. So, notice that with a set of nonlinear equations, you could have many more, a larger variety of types of solutions. So you could have, in this case, 0, 1, 2, 3, 4 solutions. And so if you have systems of nonlinear equations, it's not just 0, 1, or infinity. It could be other things. So let's recall also the techniques for solving systems of linear equations. So the techniques were graphing, substitution, elimination, the matrix methods, and determinants. Okay, well, for solving systems of nonlinear equations, well, certainly graphing is out of the question. There's no way you're going to be able to graph these, systems of nonlinear equations and have any good idea where they're intersecting. Certainly the matrix and determinants, you do not have those for nonlinear equations. So the only possibilities are substitution and elimination. It's mostly elimination that we'll be using, sometimes other things, but mostly elimination. And so let's do some examples. Let's say on page 620. Oops. Let's do problem number 1. Y equal x squared. And maybe I'll name this something. Let's say R1. Y equal x squared. R2. Y equals 2x minus x squared. So both of these are parabolas. And so we have here the case of two parabolas. Okay. So we could have, well, no solution. One solution. Well, maybe I'll have them going other directions. It'll look a little nicer. So one solution. Whoops. Let's try this again. So no solution. One solution. Two solutions. Of course, you could have an infinite number of solutions also, if they were the same. Okay, so those are the possibilities. 0, 1, 2, or an infinite number of solutions. So I guess I'll just substitute. So I'll substitute R1 into R2. And so x squared is equal to 2x minus x squared. Let's add x squared. subtract 2x from both sides of my equation. Okay, so let's subtract 2x, add x squared to both sides of my equation. And so I have 2x squared minus 2x equals 0. Factor 2x by the zero factor property. Set each factor to 0 and solve for x. And so x is equal to 0, or x is equal to 1. Well, let's use, I don't know, let's say R1. Let's use R1 to figure out the corresponding y value. So y is equal to x squared. So that says that one solution is 0, 0. Y is equal to x squared. So my other solution is 1, 1. So in this case, I have 2 points of intersection, the point 0, 0 and the point 1, 1. Let me do, let's say, problem number 4. Please note that when you solve these systems of nonlinear equations, you must write them as ordered pair solutions and not just saying x is 0, y is 1, things of that sort. 4. So let me do problem number 4. And so y equals negative x squared plus 5x minus 4, and y plus x plus 4 equals 0. Okay, so this is actually the case of a parabola and a line. So I have here a parabola and a line. So I could have a parabola and a line, so no solution. I could have a parabola and a line intersecting at one solution, or a parabola and a line intersecting at 2 points, so I have 2 solutions. So let's substitute R1 into R2. Since R1 is solved already for y. And so if I do that, I get negative x squared plus 5x minus 4. Substituting for y, negative x squared plus 5x minus 4 plus x plus 4 is 0. So I just substituted for y here, R1. Well, I get a negative x squared, combine like terms. 5x plus x is 6x. The 4's cancel, equals 0. Let me factor out a negative x. So negative x times x minus 6 is 0. So again, let me use the fact that this has characteristic 0. And so by the zero factor property, I have that minus x equals 0, or x minus 6 is 0. Divide by -1. Add 6. And so x is 0, or x is 6. I guess I'll use R1. So let me use R1 to calculate y. So y is equal to negative x squared plus 5x minus 4. So y is equal to 0 minus 4 is a negative 4. So 0, negative 4 is one solution. And y is equal to negative x squared plus 5x minus 4. So y is equal to a negative 36 plus 30 minus 4. So y is equal to a negative 10. And so we have 6 negative 10 is also another solution. So in this case, we have two solutions. Again, the line and the parabola intersect at the points 0, negative 4, and 0, negative 10, and 6, negative 10. Let me do problem number 14. X squared over 12. Oh, let's call this R1. Actually, let me not call it anything yet. So, x squared over 12 plus y squared over 16 is equal to 1. And 3x squared over 35 plus 2y squared over 35 equals 1. Let me actually simplify these first. So let me multiply both sides of my equation by 48. And so I get, and maybe I'll call that R1. 48 divided by 12 is 4, x squared. 48 divided by 16 is 3, y squared equals 48. So I'll call that R1. And let's do R2. Let me multiply by 35. So the 35's cancel. So you get 3x squared plus 2y squared equals 35. And so, actually, from the first way we wrote it, you notice that these are two ellipses. So this is the case of two ellipses. So I could have, well, no solution. The case where you have, well, an ellipse and another ellipse. You could have one solution, an ellipse just touching another ellipse. You could have the case of two solutions. Ellipse another ellipse. You could have the case of 3 solutions. Let's see, ellipse, ellipse. So 1, 2, 3. It doesn't look very good, but 3 solutions. Or you could have the case of 4 solutions. So, ellipse, one, two, three, 4 solutions. Okay, so and of course you could have infinite number of solutions. We have ellipse and the other ellipse. Okay, so those are the possibilities. Those are the possible number of solutions. Okay, so let me write down my equation again. Well, let's solve this system. So I guess I will eliminate y. So let me multiply the first one by 2, negative 2. And so let's do a negative 2, R1, and a 3, R2. Okay. And so if I do that, I get negative 8, 6. Negative 8 x squared minus 6y squared equals negative 96. And multiply the second equation by 3, so 915. 9 x squared plus 6 y squared equals 105. So let's add these. So if I add these equations, I get, well, x squared equals 9. Let's substitute, I guess, into R2. So I have 3x squared plus 2y squared equals 35. Subtract 27 from both sides of my equation. So I get that 2y squared is equal to 8 divided by 2. So y squared is equal to 4. So now let's list all of our solutions. So I have, well, from here, I get x is equal to plus or minus the square root of 9, which is 3. From here, I get y is equal to plus or minus the square root of 4, 2. And so, when x is negative 3, y could equal negative 2 or positive 2. When x is positive 3, y could equal negative 2 or positive 2. So notice in this case there are 4 solutions. So for each x, I get 2 solutions corresponding to the fact that I have 2 different y's. And so there's a total of 4 possible solutions. Okay. Let me do problem number 18. And so in this case, I want to graph an inequality. X squared over 36 minus y squared over 36 is greater than 1. Okay, and so notice that this will be, well, let's look at the boundary line. The boundary line is just x squared over 36 minus y squared over 36 is equal to 1. And so that's a hyperbola. Okay. This hyperbola is centered at the origin. A is 6. B is 6. I can figure out that the that C, the distance from the center to the foci, is 36 plus 36, 72. So the square root of 72, which is 6 rad 2. But we don't really need that. Let's draw the solution here. Okay, so this is going to be 6. That's big. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Oh, that is big. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so the bounding rectangle will look as follows. So this is my bounding rectangle. Let's draw the diagonals of the bounding rectangle, which are my asymptotes. Oops. Okay. The x is the one that has the positive. And so I have here my vertices. And this is a greater than. It has no equal sign. So I know that my boundary line will be dashed. So let me draw a dashed line for the, let's see how I can draw this as best I can. Okay, so it's going to approach here. Okay. Let's do that to the other side. As best I can. Okay. And now let's check where this is true. If it's true inside of the hyperbola, if it's true on the outside of the hyperbola. So let's check. Let's say at the origin. So let's check if the inequality is true at the origin. So is 0 squared over 36 minus 0 squared over 36, is that greater than 1? Is 0 greater than 1? No. Okay, therefore, I will shade where it is not, does not contain the origin, and so I'm going to shade out here as best I can. Okay, there. So this is my solution. And let's see if I can draw the other side. Again, as best I can. And you notice that, again, the boundary line is dashed. Maybe I'll just do it like that. Okay. And so, let me indicate that this is the solution by writing something. So let me say that this is my solution. So both of these, even though the solution is not connected, it's all part of the same inequality. Okay. Um, any questions about that? So if you shaded this, so it keeps going on forever, obviously, the shading. I just shaded a small portion of this. Okay, so that really finishes off section 14.5. Let me go on to, so that, and that finishes off chapter 14. Yeah, let me delete this page. I didn't really need it other than using it so I could draw. So delete. Okay, there. Okay, so that finishes off chapter 14. Let me start chapter 15. So chapter 15 is on sequences, series. So chapter 15. Sequences. Do you have to draw? It is a good idea that you, again, you know, it's a very crude sort of, if you looked on the last thing, I just crudely drew the number of solutions. It's a good idea to do that because if on the sudden, if you get something that's not possible, say, you know, you find 4 solutions, but it's only possible to get 2 solutions, then you know you've done something wrong. So I probably will not take off points on an exam if you don't do it, but I think it's a good idea for you to do it anyway, even though I may not take off points. Okay? So chapter 15, sequences, series, and the binomial expansion. Okay. So section 15.1 is on mathematical induction. So, there are many things in mathematics where we try to show that things are true for, let's say, all natural numbers. And so you might think that if you showed something is true for a lot of numbers, maybe it's true for everything. And that's not always the case. So it turns out that, you know, so problems with mathematics or, you know, mathematical proof. If you say that something is always true, then you must show that it is true for all cases, not just some cases. So, an example of this could be, let's say, Merton's conjecture. So, Merton's conjecture was some statement, and it was conjectured. So, it was conjectured to be true. And this was, I believe, in 1885. And it was verified. To be true. Well, they, looked at the first few cases, and then, eventually computers came around, and it was verified to be true for, I believe it was 100 billion for the first. $100 million cases. So they looked at, it's true for the first case, second case, all the way up to the first 100 million cases. But in 1985, it was shown that the conjecture was false. So even though they were able to verify the first 100 million cases, it turns out that actually it didn't hold for every number. Eventually there will be cases where you can find that it doesn't work. So the problem is that you can't just sort of say, well, I think it works or whatever. You've got to show that it works for everything. Okay? And so one of the first ways of doing that, well, they had several different ways of proofs. Proofs by contradiction, proof by construction. One proof is proof by mathematical induction. And so probably the first one to do this was in the 10th century, Al-Kharajhi. He was a Persian. And so mathematical induction. So the idea of mathematical induction can be thought of as a game of domino. Well, not the game of dominoes, but what people normally do when they're a little child and they're given dominoes by their parents. Usually they don't know how to play dominoes, so instead of actually playing dominoes, what they do is they, being nice and destructive, decide that they will line up dominoes and just have them fall over one after another. So, what's the idea behind the dominoes, right? Well, the idea is that you have one domino and that causes the next domino to fall. And if you if the first domino falls, then that causes all other dominoes to fall since the first one fell. And if one domino falls, then the next domino falls. Therefore, it must be that all dominoes fall. And that is really the idea of mathematical induction. And if so I'll just do this in mathematical sort of terms, the idea of dominoes. So if a given statement Pn is associated with every natural number n. So basically what we're saying is that P sub n corresponds to the nth domino. And so and of course we're very bored, so we line up an infinite number of dominoes. And so P sub n says, well, that's the nth domino. Then the statement Pn is true for every natural number n, provided that the following conditions hold. So first, well, P sub 1 is true. So that says that the first domino falls. Second, Pk being true implies that Pk plus 1 is true for any natural number. Okay. So this says that if you have a domino, say the kth domino, then the next domino will fall, the k plus first domino. So if you have any two consecutive dominoes, then having the first of those dominoes falls causes the next domino in line to fall. And so the very first domino falls, and for each domino, the next domino in line, let's say that again. If the first domino falls, and if the any domino in line being true causes the next domino line to also be true. So if any domino falling causes the next domino line to fall, then all dominoes will fall. Then all dominoes are true. All statements are true for every natural number n. So therefore, if these hold, then P sub n is true for every natural number n. So let me give you some steps. So let me codify the steps to a mathematical induction proof. So the first step, state the initial condition. Tell me what P1 is. 2. Show that the initial case, well, maybe I called it case here, that the initial case is true. Okay. So now you're showing that P1 is true. 3. State the induction case. So PK. So state PK. 4. Show. Well, actually, I guess the induction case is really show state PK imply PK plus 1. Show that the induction case is true. So you want to show that PK plus 1 is true. So the induction case says PK true implies PK plus 1. The showing the induction case is true says to show that that implies that PK plus 1 actually is true. And then 5, well, just write down your conclusion. So 5, write the conclusion. That mathematical induction shows that the statement is true for every natural number. So let's do an example. Use this is Math 125. So mathematical induction is Math 125. Yes. all of chapter 13, 14, and 15 is, ooh, no, 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 no. Uh, oh. The Fortunarian is after this at 2 o'clock, not at this time. Okay. Uh, yes. Okay, sorry. Sorry, I have more than one online session today, and they were in the wrong session. Okay. Example. Use mathematical induction to show, to prove that 1 plus 2 plus 3 plus. No, let's do this. No, I'll do it this one. 1 plus 2 plus 3 plus n. Show that this is equal to n plus 1 over 2. Okay, so let's do this. Now, I usually write down the letters PF and a little colon, and this just says I'm starting. So start of proof. That's all this sort of indicates. Because a lot of times students have a hard time figuring out where the proof even starts or ends. So they don't even know where it starts or ends. So put PF to say I'm starting. Okay. So now let's do the initial case. And so the initial case is, well, I want to show that 1 plus 2 plus 3 plus dot 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 n is equal to n over n plus 1 over 2 when n is equal to 1. Thus, we wish to show that 1, because I'm letting n equal 1, so that means you just have 1, is equal to 1 times 1 plus 1 over 2. Okay, so let's see if that's true. Well, what's 1 times 1 plus 1 over 2? Well, 1 plus 1 is 2, divided by 2 is 1. 1 is equal to 1, so therefore, we have shown that 1 plus 2 plus 3 plus is equal to n plus 1 over 2 when n is equal to 1. So now let's do the induction step. So induction case. So let's write down the induction hypothesis. So we wish to show that if 1 plus 2 plus 3 plus k is equal to, so instead of writing n, I'm going to write k. So k plus 1 over 2 is true then this implies that, well, 1 plus 2 plus 3 plus, let's go all the way up to k plus 1, that this is true. Well, where are you place n in the formula? By k plus 1. So let's write here k plus 1 times, well, n plus 1 over 2. And so, if I'm able to show that this is true, then I've shown the induction step in the induction case. And so, well, my induction hypothesis stating that this is true implies that, well, 1 plus 2 plus 3 plus k plus 1, so I just go out one further, is equal to, well, this I know is equal to k plus 1 over 2. The next term is just k plus 1. Let me add these by finding a common denominator, 2. And so I get, this is equal to, let me multiply the k inside the parentheses, k squared plus k. Let me multiply the 2 inside the parentheses, 2k plus 2. Well, I can certainly add numerators, since I have a common denominator. So k squared plus k plus 2k is 3k plus 2 over 2. Now I can factor. Well, this factors nicely into k plus 2. And let's write it this way. K plus 2 times k plus 1. But let me write k plus 2 as k plus 1 plus 1. Well, if I look here, that is exactly what I wanted to show. So therefore, I have shown that if 1 plus 2 plus 3 plus k is k plus 1 over 2, if for k a natural number, if this is true, then 1 plus 2 plus 3 plus, then I've shown that this holds for the case of k plus 1. Therefore, by the principle of mathematical induction we have shown that for every natural number n the following is true. One plus two plus three plus n is equal to n plus 1 over 2. And now I usually write at the end QED, and so this means this is the end. This is the end of the proof. So we usually write QED just so that we know that we're done with what we've stated. We're done with what we wanted to prove. Okay. Let's do, let's say on page 635. Let me do problem number 10, which says that that 5n minus 1 is divisible by 4 for all natural numbers n. So let's show this. In other words, oh, yes. Okay, so let me let you guys for 1 second. Sorry about that. Catch up. Okay, so the fact that I have that 5n minus 1 is divisible by 4, this means that for every natural number n, there exists a natural number let's call it A, such that 5n minus 1 is equal to 4a. Okay, so let's do the proof. So let me write down the initial case. So what we want to do is we want to show that there is some number a such that 5 to the 1 minus 1 is equal to 4 times a. Well, we wish to show that there is a natural number a, that there exists a natural number a such that five to the n minus 1 is 4a when n is equal to 1. So let's do that. So 5 to the 1 minus 1 is 5 minus 1, which is 4. And well, 4 is equal to 4 times 1. So therefore, thus, 5 to the first minus 1 is equal to, well, maybe I'll write this way. 5 to the n minus 1 is equal to 4a when n is equal to 1 and a is equal to 1. So there is some natural number, 1, such that 5 to the n minus 1 is equal to 4a when n is 1. Okay, so that's the initial case. Let me do the induction case. So the induction case is going to be very similar. We want to assume that there exists some natural number a such that for some natural number k, 5 to the k minus 1 is equal to 4a. I then want to show that that implies that there exists some natural number b or whatever, or capital A, such that 5 to the k plus 1 minus 1 is equal to 4 capital A. And so, let's do that. So we wish to show that there exists a natural number well, that if, let's do it this way, that if that for a natural number k and a, if 4 to the k minus 1 is equal to 4a, then there exists a natural number and I guess I'll call it capital A, such that 4 to the power k plus 1 minus 1 is equal to 4a. If I do that, then I've shown the induction case. Okay, so let's do this. Well, the induction hypothesis is that 4 to the k. Oh, why am I writing 4s? That is a typo. No, 4 is correct there, but the 5 to the k. I said 4 to the k, didn't I, even? 5 to the k plus 1 minus 1 is equal to 4a. Okay. By the induction hypothesis, we have that 4 to the k minus 1 is equal to 4a. So for any natural number k, we assume that there exists some natural number a, such that 5 to the k minus 1 is equal to 4a. Let's add 1 to both sides. And so this says that 5 to the k is equal to 4a plus 1. Okay, so now let's look at 5 to the k plus 1 minus 1. This is the same as 5 to the k plus 1 minus 1. So this is equal to, well, 5 to the k is 4a plus 1. Multiply the 5 inside the parentheses. So this is equal to 20a plus 5 minus 1, which is 20a plus 4. And so let me write this as factor out of 4. So this is 5a plus 1. Well, since a is a natural number, then 5a is a natural number. If natural numbers are closed under multiplication, a natural number times a natural number is a natural number. So if you have some number like 12, 5 times 12 is certainly going to be a natural number, 60. So if you have some natural number a, then 5 times a is certainly a natural number. And since 5a is a natural number, then adding 1 to it is still a natural number. Again, the natural numbers are closed under addition. And so if you have some number like 32, then 32 plus 1 is also a natural number, 33. Okay, and so therefore 5a plus 1 is a natural number. Let a equal 5a plus 1, then a is a natural number, and we showed that 5k plus 1 minus 1 is 4a. And that's what we wanted to show. Thus, we have shown that 5k minus 1 equaling 4a implies that 5k plus 1 minus 1 is 4a, where a is was 5a plus 1. Therefore, goes, and A is a natural number. Therefore, so we have shown that the induction case works. Therefore, by the principle of mathematical induction, we have shown that for every natural number n, there exists a natural number A such that five to the n minus 1 is equal to 4a. And that's what we wanted to show. So I am done. Let me wait at least a few seconds in case people are still writing. Okay, so let's do another one of these. Should be identical, really. Problem number 11. I want to show that 7n minus 1 is divisible by 6 for every natural number n. So in other words, for every natural number n, there exists a natural number a such that 7n minus 1 equals 6a. Okay, so let's do that. So first, let's write down the initial case. Well, we've done it before, so 7 to the first minus 1 is just equal to 6, which is 6 times 1. So therefore, so this shows that there exists at 7 to the n minus 1 is equal to 6a for n equaling 1, where a is equal to 1, which obviously is a natural number. Okay, let's do the induction case. So let's assume that there exists some natural number a, so that 7 to the k minus 1 is equal to 6a. Let's add 1 to both sides. So 7k is equal to 6a plus 1. And so this implies that, so let's look at the k plus first case. 7k plus 1 minus 1 is equal to 7k times 7 minus 1 equals 7k we found was 6a plus 1. Multiply the 7 inside the parentheses. So this is 42a plus 7 minus 1. So 42a plus 6. So I can factor out a 6. And so let capital A equals 7a plus 1. Since a is a natural number, then 7a is a natural number, again, by the closure property for multiplication of natural numbers. And therefore, 7a plus 1 is a natural number, again, since natural numbers are closed under addition. And so I've shown the induction case. So therefore, by the principle of mathematical induction, seven n minus 1 is divisible by 6. For all natural numbers n. So I am done. Please note that this is the minimum amount of work that is necessary to get full credit for this proof. So in the previous steps, I sort of gave you words to explain what I was doing. Now, if on an exam gave you this problem, this would be the minimum number of steps to get full credit. And if you didn't show all these steps, you would not get full credit. Okay, let me do, let's say, problem number 6. For every natural number n, I want to show. So I want to show here that 3 to the n plus 1, 3 times 10 to the n plus 1 plus 8 times 10 to the n plus 7. I want to show that that's divisible by 9. And so I want to show that for every natural number n, there exists a natural number a such that three times 10 to the n plus 1 plus 8 times 10 to the n plus 7 is equal to 9 times a. Okay, so let's do that. So let's do the initial case. So let's look when n is equal to 1. So let's look at the case where n is 1. Why do I keep doing that? So let's look when n is equal to 1. So this is equal to 3 times 10 squared plus 8 times 10 plus 7. So 300 plus 80 plus 7. So 387. So this is equal to 9 times 43. And so this is equal to 9a, where I've let a equaling 43, and of course 43 is a natural number. So thus I've shown the initial case. Let's do the induction case. Okay. So again, I'm writing down here sort of the minimal things that you would need. Oh, I actually didn't even write that down. So this is the minimal amount you need to write. Next, let's assume the induction hypothesis. So let's assume that 3 times 10 to the k plus 1 plus 8 times 10 to the k plus 7 is equal to 9a for some number a. Let me subtract 8, 7, 8 times 10 to the k minus 7 from both sides. And so I have that 3 times 10 to the k plus 1 is equal to 9a minus 8 times 10k minus 7. Okay. So now let's look at the case when n is k plus 1. And so let's look at 3 times 10 to the k plus 1 plus 8 times 10 to the k plus 1 plus 7. Well, this is the same as 3 times 10 to the k plus 1 times 10, just by properties of exponents, plus 8 times 10 to the k plus 1 plus 7. Let's replace 10 to the k plus 1 by the following. 9a minus 8 times 10k minus 7. And well, what I have remaining is, so I replace this first part by that, but I still have a 10 here. So let's multiply by 10 plus 8 times 10 to the k plus 1 plus 7. So let's multiply the 10 inside the parentheses. So this is equal to 9 times 10 is 90a minus 8 times 10k times 10 is 10 to the k plus 1 minus 70 plus 8 times 10 to the k plus 1 plus 7. Notice that the 8 times 10 to the k plus 1's cancel. And so I get 90a plus 7 minus 70. So minus 63. So this is equal to, factoring out a 9, 10a minus 7. So in this case, let a equal 10a minus 7. So this is equal to 9a. Well, since a is a natural number, then 10a is a natural number. By again, the closure property for natural numbers, the closure property of multiplication for natural numbers, and then 10a minus 7 is a natural number because if n is a natural number, then 10a, which has got to be at least 10, some multiple of 10, so 10, 20, 30, 40. If I subtract 7 from it, well, notice that that 7 is smaller than 10. And so by the closure property for addition of integers, 10a minus 7 is an integer, but since 10 is greater than 7, then it'll actually be a positive integer, a natural number. And so a is a natural number. And so therefore, we've shown, that the induction case holds. Since the initial case and the induction case held, then I've shown that 9, that whatever, now I forgot, 3 times n to the, no, I wrote it again wrong. 3 times 10 to the n plus 1 plus 8 times 10 to the n plus 7 is divisible by 9 for every natural number n. And that's what I wanted to show. Okay. So, let me just check. Are we supposed to end at 1? I think we are. To the moderator. Sorry. Is this over at 1? Yes. Okay then. So I guess, yeah, I do 115. Oh, it's over at 115. At 115. Okay, so that means I have 15 more minutes or 20 more minutes. Okay, so I'll continue for 20 more minutes. Sure. Yeah. I just don't want to go over on your time. Okay, so um, let me. So I have 20 more minutes. Okay, so let me do some constructions. So the construction for sets of numbers. Okay, so first let's construct the set of real numbers. The set of natural numbers, sorry. Let's construct the set of natural numbers. So with the set of natural numbers, there are these axioms called the Peano axioms, named after the person Peano. I forget his first name. So the Peano axioms. They state the following. There exists some number, 1, and that number 1 is a natural number. So there's some special number, I'll call it 1. Next, there exists some injective function, S, that goes from the natural numbers to the natural numbers. It'll be injective, but it will not be surjective. This S function is called the successor function. It can be thought of, it's the next number. So if I look at the number 12, then the successor of 12 is 13. Okay, and so it's the next number, the next natural number. Next, 1 is very special. It doesn't have, it doesn't come, there isn't a number whose successor is 1. So 1 is the smallest natural number. So there does not exist a natural number such that its successor is 1. And so 1 can be thought of as that special smallest natural number. And lastly, and with all of just these 4 ideas here, these 4 axioms, we can construct all the natural numbers from these. So the last axiom is the mathematical induction axiom. So this says that if A is some subset of the natural numbers such that 1 is in this set, the initial case, and n being in this set implies that its successor is also in the set. That's the induction case. So that we have the next guy. Then this set N, this set A, is just the set of natural numbers. So if the first thing is in your set, and if some natural number in the set implies that its successor is in the set, then that set is a set of all natural numbers. Meaning, if the first thing is true, and if the kth object being true implies the k plus first object true, then it's true for all natural numbers. Now, of course, this is a little bit more primitive than the version of the mathematical induction that I gave you, because it's so maybe I'll sort of state here, this is principle of mathematical induction. So this is more primitive because we're really just looking at sets. But so this says there is a natural number 1. This says that 1 is the smallest number, smallest natural number. I haven't told you what big and small are yet, but and then every natural number has a successor, has a next consecutive natural number. So it has the next number, and we call this the successor. Okay, so I can show that it's allowed that I can give definitions that are recursive. Okay, just these piano axioms allow me to do that. It's not that difficult to show, but we'll just assume that I can show recursive definitions. I can give recursive definitions. So I have numbers, right? But I haven't told you what to do with these numbers. So let me define addition. So if I have some natural number n, then I'll define n plus 1 as the successor of n. Next, if I have some natural number n and some natural number m, then I'll define n plus the successor of m as being the successor of n plus m. Next, let me define multiplication. Maybe I'll give you these definitions first, and then I'll give you an example. So, it's very similar to the definition of addition. If n is a natural number, then n times 1, I'll define that as n. If n is a natural number, and if m is a natural number, then I'll define n times the successor of m. So that's m plus 1, so that's got to be n times m plus n. Just thinking of the successor of m as being m plus 1. And I'll define exponentiation in a similar sort of fashion. So let me assume here A is some natural number, n. Then I'll define A to the first as A. If n is some natural number, then I'll define the successor A to the successor of n as equaling A times A to the n. Okay, good. So notice that addition is defined in terms of successors. I know what successors are. That multiplication is defined in terms of addition, and we know what addition is. And exponentiation is defined in terms of multiplication, and we know what that is. And so we can determine each of these. So let me give you some examples to show you how that works. So, and this is sort of a good way of seeing how recursive ideas work, which is important in this section. And really, that's the idea of mathematical induction. Okay, so let's do the following. Show. So maybe I'll call this example 1, even though I probably had further examples before, but show that 3 plus 1 equals 4. Okay, well, oh, and by the way, I guess I should say this before even I give you the example. Notation. Define 2 as the successor of 1, 3 as the successor of 2, 4 as the successor of 3, etc. So define all the usual numbers as the successors. You know, successor 3 is successor of 3 is 4, successor 4 is 5, successor 5 6, etc. And now let me get to an example. And so I want to show that 3 plus 1 is equal to 4. Well, let's look at 3 plus 1. Well, 3 plus 1 is, by definition, n plus 1 is the successor of n. So this is the successor of 3, but the successor of 3 is 4. And you're done. By the way, 1 plus 3 would be shown in a different way. So please note that 3 plus, I sort of gave it to you in a nice way because we haven't shown yet that addition is commutative or anything else. It will be, but we haven't shown it yet. Okay, so let me do another example. So you can only use the properties of Peano's axioms and the definition of this recursive definitions given above. So let's do the next one. Let's say I want to show that 3 plus 2 is equal to 5. So let's show that. Well, since 2 is the successor of 1, right? So I had 2 successive 1. Then 3 plus 2 is the same as 3 plus the successor of 1. But, well, we've shown that n plus the successor of m is the successor of m plus m. And so this is the same as the successor of 3 plus 1. But 3 plus 1, by example 1, so this is by the definition of addition. This is by the fact that 2 is the successor of 1. So by the example 1, I know that 3 plus 1 is 4. And well, that's equal to 5. And this is due to the fact that 5 is the successor of 4. Again, that's our notation. That's what we call the successor of 4. Good. So that means I'm done. I've shown that 3 plus 2 is 5. Let's do one more of these. Let's show that 3 plus 3 is equal to 6. Okay. So let's see what I have to do. So proof. Well, notice that what I wanted here, I wanted to do a 3 plus 2 was something involving successor. So I used the fact that 2 was the successor of 1. So now I'm going to look at this. I wanted to do, well, let's see, what's the successor of what number is 3? Well, 2. So since the successor of 2 is 3, then we have the following. 3 plus 3 is the same as 3 plus the successor of 2. Okay, this is since 3 is the successor of 2. So this is equal to, well, by definition of addition, of natural numbers, this is the same as the successor of 3 plus 2. But by example 2, I know that 3 plus 2 is 5. And well, the successor of 5 is 6. Again, by our notation that 6 is the successor of 5. And so I'm done. Okay, so let's show example 4. $115 already. Okay, example 4. Let's do 3 times 2 is 6. This is PC noise. I don't know. I don't hear anything on my end. Okay, so proof. Okay, so I have that. I want to look at the successor of 2, so a successor of 1. So since 2 is the successor of 1, then 3 times 2 is the same as 3 times the successor of 1. This is chapter 15, section 15.1, and we're almost done. Okay, and so the successor of 1, and so by definition of multiplication, this is just 3 times 1 plus 3. Okay, and so, well, 3 times 1, hopefully I showed that back. Oh, I showed 3 times 2 is 6. Oh, successor of 1, yeah. And so, well, this is equal to 3 times 1 by, so this is the, I'm using the fact that this is, the 2 is the successor of 1, and this is the definition of multiplication. Okay, next, I want to show that 3 times 1 is 3. Well, this is again by the definition of multiplication. So this is equal to 3. And so if I look here, any natural number times 1 is just that natural number. So 3 times 1 is 3. And by example 3, this is 6. And that finishes off. This is section 15.1. Yes. This is section 15.1. Okay, so I guess that's it for today. And then we'll continue with this tomorrow. Same time, yes. Same time. Yeah, so you'll be able to find this on cccconfer.org, the same place you're at. It's just that when you go into the very first part of it, if you look, it says watch a recording. Just click on that and look for my name. Okay. I'll also post this to YouTube, and I will, in the announcements, tell you where it is. I'll put the link on YouTube.